Hello everyone, today we'll talk about the problem minimum number of days to make m bouquets. We're given an array of flowers and you want to create m bouquets. Every bouquet is created by taking k adjacent flowers from our array. However, the problem is that those flowers haven't bloomed yet, and for every flower we know the first day at which it will bloom and become available from then onwards, right, to become a part of a bouquet. So essentially you want to say what is the minimum number of days that we have to wait so that we can create m times m disjoint slices of length k of the original array such that all the numbers in the slice are not bigger than the number of days we've waited. At first it may seem difficult to come up with something to do in this problem, but after some thought you might come up with the idea that we can create a brute force algorithm that will just check all the possible days, or maybe all the interesting days, because the only interesting days are those that are unique values in our bloom day array, and just check if it's possible to create those m bouquets then. Now, is it possible, and is it simple to check if it's possible after some days to create m bouquets? And indeed it is simple, because then we have some intervals consisting of flowers, so those empty spaces between our flowers that haven't bloomed yet. We have to create m intervals here, each of length k, and they have to be disjoint. And we can, for instance, do it greedily. So we try to take, let's say, this interval first, and maybe this part is left over. Here we cannot create an interval. Here we create one interval, we can create another interval. Here this part remains. And it's easy to see that this indeed will find a solution if a solution exists. So we can now, in time proportional to the number of different values in our bloom day array times the length of the bloom day array, so essentially in n squared, we can solve this problem. And to get an optimal solution, one that is n log n, we can use the very standard trick, which is binary search on the answer. Because since if it's impossible to create those m bouquets at day d, then it's of course even more impossible to create it any earlier. And if it's possible to create it at day d, then it will keep being possible into the future, because new flowers can appear but no flowers can disappear. Which means that we can guess some day at which maybe it's already possible, and if it's not possible at that day, now we have halved the space of possible days where our answer can lie. And if it's possible at that day, then maybe it's also possible earlier, but we've also halved the number of possibilities. We only have to check the first half. So if this is the whole, let's say, timeline, then first we check this one. If it's possible here, we check this one maybe. If it's not possible here, then the smallest day is here, and so on. And after all that, we'll settle on a single day, and that will be the answer. And let's jump into the implementation. I typically implement binary search in a different way, which we'll see in code. First of all, our task is to find the last day for which it's impossible to create the bouquets, because the day after that will be the first day where it's possible. Or maybe it's still impossible, but that means that there is no answer, so we have to return -1. So we'll need an auxiliary function that will check if it's possible after these many days to create m bouquets. Now checking that is very simple. We just go through all the bloom days of our flowers. If at any point the flower hasn't bloomed yet, then you have to forget what we've seen previously. Otherwise, we remember that now we have seen one more consecutive flower. And if we have seen exactly k consecutive flowers, then we can create a bouquet from them. So the remaining bouquets to create is decreased. And the day is bad if some bouquets remain to be created after we go through all the flowers. So now we have this auxiliary function. We can binary search on values of that function. So we start our answer with 0, day 0, for which we know that the answer is it's impossible. We create some maximum answer, so that if no answer exists and we have to return -1, we don't search indefinitely. And instead of normal binary search, I typically do binary search from the left by jumping to the right. First by making big jumps, then smaller jumps, smaller, smaller, and so on. So we'll take a jump to be equal, let's say, to half the max answer, and we'll be jumping forward for as long as it's possible. So for as long as after, let's say now we wait 0 days, and the first jump is 8, so we check if after 8 days it's still impossible. So this would be 8, and we check if it's impossible. If it's impossible, then we remember that it's impossible after 8 days, and now we try 16, and so on. And then if it's impossible after 8 days, but possible after 16, then we have to check 8, so that's our all answer, plus 4. And then plus 2, and maybe it's possible after plus 2, but not possible after another plus 2, so we check plus 1. And after that, after we go through the jumps of length 1, then we are guaranteed that we have found the last index at which it's impossible to create m bouquets. And of course, after every step, we divide the jump length by 2, which is why we have only a logarithmic number of steps. And then we just check if the answer, because the old answer was the last index at which it's impossible to create m bouquets, so the next index should be the first one where it's possible, so we check if it's possible. If not, we return -1, otherwise we return that index.